Hi, Upward Bound Chemistry, Bonding, and Naming for Day 2. First, let's talk about electronegativity. You picked up a sheet that shows the electronegativity of every element. Electronegativity is a measure of the ability of the atom in a chemical compound to attract the electrons from another atom of the same compound. So there are three basic kinds of bonds, and actually when we bond things, we will put them into just ionic and covalent. However, those polar covalents, you have to check their oxidations in order to figure out if it is going to bond covalently or ionically. And I'll show you how to do that. So for ionic, the electronegativity is supposed to be between 1.7 and 3.3. Polar covalent is between 0.3 and 1.6, and nonpolar covalent is supposed to be between 0 and 0.3. You are going to want to add that to that electronegativity chart I gave you. So types of bonds. Again, you have ionic. It's an attraction between positive and negative ions, those oxidations, where electrons are lost and gained between metals and nonmetals. And that's not the chemical state of matter. That is bonding type. So the atoms will be classified as bonding type metal or bonding type nonmetal. Then you have covalent. That's an attraction between elements where the electrons are actually shared between the elements, and it only occurs between bonding nonmetals. So in the periodic table, you're going to add the oxidation numbers, and I realize this is a little difficult to see, but above group 1, you're going to put a 1 positive or 1 plus. Above group 2 is a 2 positive. Groups 3 through 12 have variable oxidations, but most of the time they're going to be a 1, 2, or 3, and they are always positive. Group 13 is a 3 positive. 14 is plus or minus 4. It's really hard to see there. And then 15 is 3 negative, 16 is 2 negative, 17 is 1 negative, and 18 is 0. Be sure you get those added to your color-coded periodic table. You also need to add the stair-step line. It's shown here in red. On your periodic table, the stair-step line draws a line between hydrogen and helium on the left, and then starts with a horizontal line between boron and aluminum, vertical between aluminum and silicon, horizontal between silicon and germanium, vertical between germanium and arsenic, horizontal between arsenic and antimony, vertical between antimony and beryllium, horizontal between beryllium and polonium, vertical between polonium and astatine, and that should be as far as your periodic table goes. So notice it creates a little stair step, and everything on the upper right hand side, including hydrogen, everything on the upper right hand side is considered a non-metal for bonding purposes. Okay, everything over there is a non-metal for bonding purposes. Everything else on the periodic table, okay, all of this, that's considered a metal for bonding purposes. Hydrogen, remember, is a weird element. It bonds ionically and covalently. It essentially does whatever it wants. So we'll try not to use examples that have hydrogen in them. Polyatomics, you also picked up a sheet, or it's on the back of your electronegativity sheet, that is a massive list of polyatomics. These are preformed covalent compounds with unique names and charges, and they will bond ionically to other elements and compounds. So writing ionic formulas, the positive oxidation always comes first. In a transition, the oxidation has to be given to you as a Roman numeral. The oxidations then crisscross to become the subscripts, and in polyatomics, you're going to want to use parentheses to keep the polyatomic itself together. Covalent bonds are formed in much more complicated and they're harder to write since they could share electrons between 1 and 3 electrons. So we'll only classify them using electronegativity. I'll have to tell you how many bonds you actually have in order to get them to write them correctly. So example 1, if I gave you K and P, potassium and phosphorus, first, you check the electronegativity difference. Potassium is a 0.8, phosphorus is a 2.1, so the electronegativity would be a 1.3. What type of bond is it? Well, based on the electronegativity, it's a polar covalent bond, but you also have a metal and a non-metal, so we would bond that or write the formula for that bond ionically. So the oxidation of potassium is a 1 positive, phosphorus is a 3 negative. Those would crisscross to make K3P. Example 2, if I gave you calcium and fluorine, the electronegativity is 3, definitely an ionic bond. The oxidations for calcium are a 2 positive, fluorine is a 1 negative. Those are set. They crisscross, the formula would be CaF2. We don't necessarily need the 1, but if you want it, you can have it. Finally, example 3, if I gave you barium and bisulfite, the electronegativity difference is well over 3. Okay, so when they bond, this would be an ionic bond. Anything that involves a polyatomic is an ionic bond. So the oxidations for barium are 2 positive and bisulfite are 1 negative. Notice that that formula did come directly from the polyatomic sheet that I gave you. The formula then, again, those oxidations would crisscross. You would have Ba, open a parenthesis, HSO3, close that parenthesis, 2. Okay, so now let's talk about naming. Now that you have a list of formulas, now we're going to talk about how to name those formulas. So when you name an ionic will always have a positive oxidation and a negative oxidation, known as the cation and the anion. The positive will be a metal, bonding metal, and the negative will be a non-metal. And you always have a first name and a last name. So the first name could be an element, the last name could be an element, and we use a root-eyed system to name it. The first name could also be a transition. It does require a Roman numeral. Okay, that's straight ionic. When you name with a polyatomic, you could have an element with a polyatomic or a transition with a polyatomic. And again, that polyatomic would be a negative polyatomic here. Okay. If you use a positive polyatomic, you could bond that to a root-eyed when you name it, or another polyatomic. Naming covalent rules. So you have to be given the number of elements. The lower group number goes first. The higher period number goes first if they're in the same group, and oxygen always goes last. And we're going to name these as basic covalents. We're not going to try to name them as acids or anything like that. We're just going to do basic covalent naming. Prefixes will show the number of atoms. So we never start a first name with mono. So this is your list of prefixes, 1 through 10. They're the same as they are for like polynomials and that in math and polygons in math, except for 2 is di instead of bi, and 4 is tetra instead of quad. Otherwise, they're the same as they are in math. So when you name a covalent compound, every covalent compound starts with a prefix, and then the element for the first name or the root of the element for the last name. Remember, first names cannot start with mono and last names always end in "-ide". Thanks for watching.